Hi and welcome to video 4 on the normal distribution, unit 4, topic 4, mathematical methods. So this is going to be mostly a review with some examples that will take you a bit further on the work that we did in video 1, 2 and 3. So recall that this is a bell curve, a normal distribution, and it's symmetrical. That's something that we haven't discussed. So it is symmetrical around the mean there, and the area below is obviously equal to 1. But x does exist between negative infinity and infinity, technically. Although once you go beyond the 3 or 4 standard deviations, you really are about as far away as you can get in most cases. Now, we've got first of all the 68, 95, 99.7 approximation. And here's a diagram you may wish to copy. So you could pause the video now and copy it. In essence, though, if you do the calculation, this is the probability that z is between -1 and 1, and it's about 68%. In fact, we did that in the example in video 1, and we got 68 point something percent. 2 standard deviations, 95% of the data for a set of data that's normally distributed lies within 2 standard deviations of the mean. Within 3 standard deviations of the mean is 99.7% of the data. That means there's 0.3% of the data left, 0.15 on this side and 0.15 on that side. And that's why I say that pretty much you're going to lie somewhere in 3 standard deviations either side of the mean, and some very small anomalies lie outside of that range for a large set of normally distributed data. So just recall some language and the formula. Standard scores versus raw scores, so that's Z scores versus X scores. The raw score is the actual data. It's the actual test scores. It's the actual height of people. The standardized score is the Z score, and it compares the data as a distance away from the mean in terms of the number of standard deviations measure. And of course, you'll need to know, this is the main one, that Z is equal to X minus mu over sigma. You use that most of the time, but you can transform it into this formula. So just know them both, but I'd just be knowing the first one and being able to relate that to the second one. Now, I do have a quick question for you, and it's a quiz question today. What is the tallest building in the world? And the answer is the library, because it's got the most stories. So there we go. It's a bit of information for you. Example 4. A set of raw data has a mu of 28 and a sigma of 3. Find the standard score for, and there's a whole bunch of them there, so let's just go ahead and do them. So we know the standard score, Z, is equal to X minus mu over sigma. So in the first case, this is equal to 28 minus 28 over 3, which of course is just 0. So the answer to the first one is 0. The answer to question 2, you can always pause and just check your knowledge as I do it. The answer to question 2 is the Z score is equal to 31 minus 28 over 3, and that's 1. So the answer to question 2 is 1. Question 3, Z is equal to 25 minus 28 over 3, and that is -1. So that's 1 standard deviation below the mean. 4, Z is equal to 26.5 minus 28 over 3. If you put that in a calculator, you get -0.5. So this is -0.5 standard deviations below the mean. And then we have the fifth one, Z is equal to 21.7 minus 28 over 3. That's equal to -6.3 over 3, which equals -2.1. So this is -2.1, and that's -2.1 standard deviations below the mean. And then we're going to plot each of these on the graph. So 0 is here. That's answer to 1. The answer to 2 is about here. And the answer to 3 is symmetrically on the other side. So that should be 3. The answer to 4 is here. And the answer to 5 is -2.1, so it's down here somewhere. So there's our 5 answers plotted onto our normal distribution. Now, we can use z-scores to do comparisons, and this is where it really comes into its own. Irrespective of the values of mu or sigma, if one z-score is greater than the other, then that implies that that first z-score is a situation that has done better. It's more standard deviations above the mean. And now this is a little bit like the golf compared to sports analogy. It's not always better to be a long way above the mean. Just like in most sports, it's better to have the highest score unless you're playing golf. So it's not always better to have the highest. It really depends on context. So make sure you read and understand the context. But I've got to say, most of the time it's better to have a higher z-score than a lower one. So it's usually better to be 3 standard deviations above the mean than 2. And it really doesn't matter what mu and sigma is. So let's have a look at this. For example, if you're trying to compare a maths exam result to a chemistry exam result. 28 out of 40, which is 70%, in an exam where x bar equals 24 and sigma equals 2. So this would mean that the z-score, this so-called z1, is equal to 28 minus the mean, 24, over 2, that's sigma, and that's equal to 2. That's 2 standard deviations above the mean. The second one, 37 out of 50, which is 74%, so a better percentage, the z-score, z2, is equal to 37 minus the mean, which is 30, x bar is another way of saying mu, over 5, which is sigma, and that, of course, is equal to 1.4. And therefore, the first result was actually better compared to the class or the cohort or the state or whatever it is better. If I got a z-score of negative 1.5 in each of these exams, what would my actual mark be? So remember, x, my raw score, x1 for exam 1, is equal to the z-score, negative 1.5, times by the standard deviation, 2, plus my mean. And that ends up being negative 3 plus, my mean, which is 24, plus 24, which is equal to 21. And x2 would be equal to negative 1.5, my z-score, times by my mean, which is 30, and then, times by my sigma, my standard deviation, which is 5, and then plus 30, and that comes out as 22.5. Now, this is still higher than that. It's a higher mark out of in the exam, but it's obviously out of 50 instead of 40, so that kind of technically makes it a lower percentage, but either way, they're both the same result comparatively to the class. And in a lot of cases, it doesn't matter what result you get, it depends on where you sit within a class. But then also you have some cases where you just need to pass, and that's okay. And let's look at the last section here, standardizing the normal distribution and looking at z-scores. I've got a pretty big example here that I want to run through and just make sure that you can do. So I've just lost myself. There we are. So remember that we have our mean, and then we have mean plus sigma. We have our mu plus 2 sigma, mu plus 3 sigma, minus 2, minus 3. And there's our equivalent z-scores. We use z-scores to calculate probabilities of data points likeliness based on its position. So we can convert to z-scores and then calculate probabilities of z-scores. Now, first of all, remember this rule. 68% of data lies within 1 standard deviation. And that tells me that the first one is equal to 68% or 0.68. 99.7% of data lies within 3, which tells me the second one is equal to 0.997. Now, the third one's a bit tricky. This is where you've got to start really thinking about the graphs that you draw. So if I draw a normal distribution, it doesn't have to be perfect. I'm saying, what's the probability that z is greater than or equal to 2? So there's z equals 2. There's z equals 0, and I want to find this probability. Now, what I do know from my 68, 95, 99.7 rule is that the area between negative 2 and 2, this area in green, is 95% or 0.95. And so that tells me that the probability, and watch my working here, the probability that z is greater than or equal to 2 is equal to 1 minus the probability that z is between -2 and 2, and then the leftover here has to be divided by this side and this side, and it's symmetrical, so divided by 2, and that equals 1 minus 0.95 divided by 2, which is 0.25, and that's wrong. 0.025, of course, is right. 2.5% of data exists above 2, 2.5% exists below -2, and 95% exists in the middle, and that makes 100% in total. So you see the calculation I just did there. D, don't ever forget that you can do 1 minus the probability that Z is greater than or equal to 2 will give me the probability that Z is less than or equal to 2. And because it's continuous, Z equaling 2 is almost impossible. That exact data point, because it's continuous, so therefore we can use greater than or equal to, or we can use just greater than. It doesn't really matter. That gives us 1 minus 0.025, which of course is 0.975. And then we have E, which is a bit of a doozy. And a few years ago I did this example and drew a great diagram, and I've just kept that diagram because I loved it so much. So here it is. You probably don't like it nearly as much as I do, but I loved it. Anyway, the probability that Z is between 1 and 2, here's my normal distribution. And this is a little bit like if you track back to our work on unit circles. I kind of think you should just draw a unit circle every time. It just makes it right, and people get the right answer. And people that don't draw them get the wrong answer more often. It's the same here. Draw a normal distribution. It doesn't have to be neat. Just draw a bell curve and mark the correct spots on it. So, here's my diagram. Here's my setup. I want to find this area in here. That is my indication. That's between 1 and 2. So the answer to this is, can I find the probability that Z is greater than or equal to 1, and can I find the probability that Z is greater than or equal to 2, and then I do orange minus purple, because this is my purple here, so orange minus purple will leave me with this bit in the middle. And I already know the probability that Z is greater than or equal to 2, I did it earlier, so I get the probability that 1 is less than or equal to Z is less than or equal to 2 is equal to the probability that Z is greater than or equal to 1 minus the probability that Z is greater than or equal to 2. And we did this one earlier. This is minus 1 minus the probability that Z is between -2 and 2 over 2. Remember when we talked about the fact that 95% of the data lies here? That leaves us 2.5% and 2.5%. Now we're going to do the same thing with the 1. In the 1 case, 68% of the data lies there, leaving us with 32% left over, so this will be 16% here. So I'll just write that up though. This is equal to 1 minus the probability that Z is between -1 Z and 1 over 2. That's equal to 1 minus 0.68 over 2 minus 1 minus 0.95 over 2, which equals 0.16 minus 0.025, which is equal to 0.135. Now this is pretty approximate because this 0.68 is a rounded value, 68%. Not significantly, but reasonably significantly. It's about 68.3% instead. So that's slightly out, but it's pretty close, and we're happy with that if we're using the 68, 95, 99.7 rule. And this, well, that could easily pop up in a non-calculator exam. So just be aware of that and be wary that it could pop up. So that's the end of our work for 17B. You should be able to do most of that now. Understand normal distribution, do the calculations for it, recall the 98, 95, 99.7 rule, determine Z-scores and raw scores, and also use that normal distribution. All the best.